The solar system is full of mysteries, but there's one that keeps planetary scientists awake at night. A perfect line of mountains running precisely along the equator of a distant moon. Not approximately along the equator. Not roughly following it. Perfectly, mathematically, impossibly aligned with it for over 1,300 kilometers. This is the equatorial ridge of Iapetus, and nothing else like it exists anywhere we've looked in the cosmos. Iapetus itself is already one of the strangest objects orbiting Saturn. It's a moon of contradictions. One hemisphere is dark as coal, the other bright as fresh snow. Its shape isn't quite spherical but slightly squashed, like a walnut. And then there's this ridge, this impossible spine of mountains that rises up to 20 kilometers above the surrounding terrain. That's more than twice the height of Mount Everest, sitting on a moon barely a third the diameter of our own. When the Cassini spacecraft first sent back detailed images in 2004, scientists genuinely didn't know what they were looking at. The ridge was so unexpected, so perfectly geometric, that it almost looked artificial. Of course it isn't artificial. But explaining how nature could build something so precise has proven remarkably difficult. Let's talk about what we actually see when we look at this ridge. It's not a single continuous wall of rock. In some places it appears as a series of isolated peaks. In others it forms a triple ridge with parallel mountain chains running side by side. The tallest sections reach those staggering heights of 20 kilometers, but the average elevation is closer to 13 kilometers. Still enormous by any planetary standard. The ridge extends for roughly 1,300 kilometers along the equator, which is about 75% of the moon's circumference. And here's what makes it truly bizarre. The alignment is almost perfect. We're talking about a deviation from the true equator of less than half a degree in most places. Whatever process created this feature had to know where the equator was. Or rather, the equator had to be defined by whatever process created the ridge. Now, how do you build a mountain range that follows a perfect geometric line across a moon? On Earth, our mountain ranges form through plate tectonics, through the collision of continental plates over millions of years. The Himalayas exist because India crashed into Asia and the crust crumpled upward. The Andes exist because oceanic crust is diving beneath South America. But Iapetus has no plate tectonics. It's a frozen world with a surface temperature around -170 degrees Celsius. It's been geologically dead for billions of years. So we need a different explanation. And scientists have proposed several, each more fascinating than the last. The first major hypothesis is called the depinning model, and it connects to one of the deepest mysteries about Iapetus, its shape. Remember that Iapetus looks slightly like a walnut. Its equatorial diameter is about 40 kilometers larger than its polar diameter. That doesn't sound like much, but for a body in equilibrium it's enormous. Our own moon has an equatorial bulge of only about 4 kilometers. Here's what this bulge tells us. At some point in its early history, Iapetus was spinning much faster than it does today. A fast-spinning body naturally bulges at its equator because of centrifugal force. The faster the spin, the bigger the bulge. Based on the current shape of Iapetus, calculations suggest it once completed a full rotation in as little as 5 hours. Today it takes 79 days. So what happened? Tidal forces from Saturn gradually slowed the Moon's rotation over billions of years, a process called depinning. But here's the crucial detail. The interior of Iapetus cooled and froze before the depinning was complete. The rigid outer shell locked in that ancient bulge, preserving the memory of a time when the Moon spun nearly 400 times faster. Now, during this depinning process, the equatorial bulge would have been under tremendous stress. The Moon was trying to relax into a more spherical shape, but the frozen crust resisted. Computer models suggest this could have created massive compressional forces along the equator, essentially squeezing the crust and forcing material upward. The ridge, in this view, is a frozen record of tectonic stress from 4 billion years ago. This explanation has elegant features. It naturally explains why the ridge follows the equator so precisely. The stress would have been symmetric around the spin axis, so the resulting deformation had to be equatorial. It connects the ridge to the anomalous shape, tying two mysteries together. And it provides a mechanism powerful enough to build 20-kilometer mountains. But there are problems. The models have trouble reproducing the exact morphology of the ridge, particularly those sections where it appears as three parallel chains. The timing is also tricky. The crust had to freeze at just the right moment, stiff enough to preserve the bulge but still warm enough for tectonic deformation. And some researchers question whether compressional folding alone could really pile up material to such extreme heights. The second major hypothesis takes us in a completely different direction. What if the ridge didn't form from internal processes at all? What if it fell from the sky? This is the ring infall model, and it proposes that Iapetus once had its own ring system. Not a permanent ring like the famous rings of Saturn, but a temporary disk of debris, perhaps created by the destruction of a small moon or the capture of cometary material. This ring would have orbited in Iapetus' equatorial plane, because that's where orbital mechanics naturally places such structures. Over time, the ring particles would have spiraled inward due to various drag forces and eventually fallen onto the Moon's surface. And where would they land? Right along the equator, because the ring was equatorial. The accumulated debris would have built up into a ridge, layer by layer, over millions of years. This model has some attractive features too. It provides a natural explanation for the equatorial alignment without requiring any special tectonic conditions. It could potentially explain the triple ridge structure if the ring had multiple components or underwent several phases of infall. And it connects Iapetus to a broader phenomenon we see throughout the Saturn system, the transfer of material between moons and rings. But the ring model also has significant weaknesses. The amount of material in the ridge is enormous, roughly equivalent to a moon about 20 kilometers in diameter. Where did all this material come from? The debris would also have impacted at high velocity, which should have spread it across a broader area rather than building a narrow ridge. And detailed analysis of the ridge's structure doesn't show the layered deposits you'd expect from gradual accumulation. There's a third possibility that tries to combine elements of both models. What if convective upwelling in Iapetus' early interior pushed warm material toward the surface along the equator? In a rapidly spinning body, the centrifugal effect is strongest at the equator, which could have influenced the pattern of internal convection. Hot material rising to the surface could have created volcanic or tectonic features aligned with the equator. This model requires that Iapetus had a warm, convecting interior early in its history, which is plausible. The Moon formed in a disk of gas and dust around young Saturn, and the accretion process would have generated significant heat. Radioactive decay of elements like aluminum-26 could have maintained elevated temperatures for tens of millions of years. But convective models struggle to explain the sharpness and height of the ridge. Convection typically produces broad, gentle uplifts rather than narrow, towering mountain chains. And the near-perfect equatorial alignment still requires special conditions. Let me tell you about some of the observational details that any successful model needs to explain. The ridge isn't uniform along its length. In the western hemisphere of Iapetus, it appears as a relatively continuous wall of mountains. But as you move east, it breaks up into isolated peaks and massifs. In some regions it virtually disappears, only to reappear further along the equator. The ridge also interacts with impact craters in revealing ways. Some large craters clearly formed after the ridge, because they've punched through it and disrupted the mountain chain. But other craters seem to predate the ridge, their rims partially buried by the elevated terrain. This tells us the ridge formation wasn't instantaneous. It took time, perhaps hundreds of millions of years. The surface composition provides another clue. Iapetus has that famous two-tone appearance, dark material covering the leading hemisphere while the trailing hemisphere remains bright. The ridge seems to have a complex relationship with this dichotomy. In some areas it's dark, in others it's bright, and the boundaries don't always align with the hemispheric division. This suggests the ridge formed before the current color pattern was established, or perhaps influenced how the dark material was deposited. There's also the question of erosion, or rather the lack of it. On Earth, a 20-kilometer mountain range would be worn down by wind, water, and ice in a few 100 million years. But Iapetus has no atmosphere, no liquid water, and no geological activity to resurface the terrain. The only erosion comes from micrometeorite bombardment, which works incredibly slowly. This is why the ridge has survived for billions of years, but it also means we're looking at essentially the original structure, modified only by impact cratering. Some researchers have proposed hybrid models that combine multiple processes. Perhaps the depinning created a zone of weakness along the equator, and then later impacts or ring infall deposited material preferentially in that zone. Or perhaps internal convection established the general structure, which was then modified by surface processes. These hybrid approaches have the advantage of explaining multiple features but the disadvantage of requiring multiple unlikely coincidences. There's also been speculation about whether the ridge could be related to Iapetus' role in the Saturn system. Iapetus orbits much farther from Saturn than the other major moons, about 3.5 million kilometers out. Its orbit is also significantly tilted, inclined about 15 degrees to Saturn's equatorial plane. These orbital characteristics make Iapetus something of an oddball, and some researchers have wondered if its formation or early evolution involved unusual processes that could explain its unique features. One intriguing idea is that Iapetus might have formed elsewhere and migrated to its current orbit, perhaps through interactions with other moons that no longer exist. If Iapetus experienced significant orbital evolution early in its history, the associated tidal stresses could have contributed to its geology. But this remains highly speculative, and the connection to the equatorial ridge is unclear. What's remarkable is how much this single feature has taught us about planetary science. The ridge has forced researchers to think carefully about the thermal and mechanical evolution of icy moons. It's inspired new computer models of tectonic processes on small, cold bodies. It's raised questions about ring dynamics and material transfer in planetary systems. A single mountain range on a distant moon has become a testbed for our understanding of how worlds work. The truth is, we probably won't solve this mystery without more data. Cassini gave us the best views we'll have for decades, and while those images are spectacular, they can't tell us everything. We don't know the detailed internal structure of Iapetus. We don't know the precise composition of the ridge material. We don't know the absolute ages of different surfaces. Each of these unknowns leaves room for multiple interpretations. Future missions could potentially resolve the question. A spacecraft in orbit around Iapetus could map the gravitational field in detail, revealing the internal mass distribution. Ground-penetrating radar could probe the structure of the ridge and underlying terrain. A lander could analyze rock samples and determine whether the ridge material matches the rest of the surface or represents something exotic. But Iapetus isn't a high priority for space agencies, and such missions remain hypothetical. In the meantime, the ridge stands as one of the solar system's great enigmas. It reminds us that even after 60 years of planetary exploration, we can still be completely surprised. We have centuries of geological understanding, computer models of extraordinary sophistication, and detailed spacecraft observations, and yet we cannot definitively explain how a line of mountains came to perfectly trace the equator of this frozen, two-toned moon. Perhaps that's the real lesson of the Iapetus Ridge. The universe is under no obligation to make sense to us. Nature can produce structures that look designed, geometries that seem impossible, coincidences that strain credulity. Our job as scientists is to keep asking questions, keep building models, keep seeking data, even when the answers refuse to come easily. The ridge will keep its secrets for now. It has held them for 4 billion years. It can wait a little longer while we figure out how to ask the right questions. 0746 And yet, the more we study Iapetus, the more questions emerge from the shadows. Consider the sheer improbability of what we're looking at. In our entire survey of the solar system, across dozens of moons and planets, we have found nothing comparable. Mars has Olympus Mons, the largest volcano. Io has its sulfur geysers. Europa has its cracked ice shell. But nowhere else do we see a mountain range that follows a geometric line with such mechanical precision. Iapetus is unique, and in science, unique is both thrilling and troubling. When something appears only once, we can't compare it to similar phenomena. We can't identify patterns. We're left with a sample size of 1, trying to reverse engineer a process that left no other traces. It's like finding a single footprint in fresh snow and trying to deduce not just who made it, but how they learned to walk. Let's dig deeper into the depinning hypothesis because the physics involved is genuinely fascinating. When Iapetus was young and spinning rapidly, every point on its equator was moving at tremendous speed. For a 5-hour rotation period, the equatorial velocity would have been roughly 130 meters per second. That's nearly 500 kilometers per hour. The centrifugal force at the equator would have been substantial, enough to noticeably reduce the effective gravity there. This centrifugal bulge wasn't just a surface phenomenon. It extended deep into the Moon's interior, distorting the entire body into an oblate spheroid. The difference in radius between equator and pole would have been even larger than what we see today, perhaps 60 or 70 kilometers. Iapetus would have looked distinctly egg-shaped, a spinning top of ice and rock hurtling around Saturn. Now, as tidal forces gradually slowed the rotation, something interesting happened. The ideal equilibrium shape began to change. A slower spinning body wants to be more spherical. But actually reshaping a moon requires moving enormous amounts of material, and that takes energy. If the interior is warm and fluid, the adjustment can happen relatively easily. The moon relaxes into its new preferred shape like a ball of dough settling on a table. But if the interior has cooled and stiffened, the adjustment becomes difficult or impossible. The moon gets stuck in a shape that no longer matches its rotation rate. This is exactly what happened to Iapetus. The outer shell froze while the moon was still spinning fast, locking in the equatorial bulge. Then the rotation continued to slow, but the shape couldn't keep up. The result is a profound mechanical disequilibrium. The frozen crust is under constant stress, like a spring held in compression. The equatorial regions, which bulge outward, are being pushed inward by the desire of the moon to become spherical. This creates compressional stress along the equator, forces that squeeze the rock together. On Earth, such compression causes folding and thrust faulting. Mountains rise as rock layers buckle and slide over each other. The Himalayas grow by this process, gaining a few millimeters each year as India continues its slow-motion collision with Asia. Could a similar process have built the Iapetus Ridge? The mathematics are challenging. 20-kilometer mountains require enormous forces sustained over long periods. The rock must be pushed up against gravity, and gravity, though weaker on Iapetus than on Earth, is still relentless. Calculations suggest that the depending stress could indeed be sufficient, but only under specific conditions. The timing has to be right. The material properties have to be right. The geometry has to be right. Some models produce ridges that are too broad and low. Others produce features that are too narrow and irregular. Getting a sharp, tall, continuous ridge requires fine-tuning the parameters in ways that make some researchers uncomfortable. When a model requires special conditions to match observations, it raises the question of whether we've really understood the physics or just adjusted our assumptions until the answer came out right. There's another subtlety that often gets overlooked. The depending model assumes that the ridge formed in response to global stress patterns. But global stress should produce global features. Why does the ridge appear prominently in some regions and disappear in others? Why are there sections of the equator with no ridge at all? One possible answer involves pre-existing weaknesses in the crust. Perhaps the ridge formed preferentially where the rock was already fractured or where the lithosphere was thinner. This would explain the discontinuous nature of the feature, but it adds another layer of complexity to the model. We need to explain not just the ridge but also the pattern of crustal weaknesses that influenced its development. The ring infall hypothesis avoids some of these difficulties but introduces others. The basic idea is beautifully simple. Rings naturally form in the equatorial plane of a rotating body because of how gravity and orbital mechanics work. Material in a ring gradually spirals inward due to various perturbations. When it hits the surface, it accumulates along the equator. No special tectonic conditions required. But the devil is in the details. How massive would this ring have been? Based on the volume of the ridge, we're talking about an enormous amount of material, roughly 10 to the 17 kilograms. That's comparable to a small moon, perhaps 20 kilometers in diameter. Where did it come from? One possibility is that a natural satellite of Iapetus was destroyed by a collision. Moons can have moons, at least temporarily, and if one of these sub-satellites was struck by a wandering asteroid or comet, the debris could have formed a ring around Iapetus. The problem is that such a collision is unlikely, and the resulting debris would have been dispersed rather than concentrated in the equatorial plane. Another possibility is that material from Saturn's own ring system somehow transferred to Iapetus. This is more plausible than it might sound. We know that material moves between Saturn's moons and rings. The dark material on Iapetus' leading hemisphere is thought to come from Phoebe, a distant outer moon, carried inward by dust dynamics. Could a similar process have delivered ring material to Iapetus' equator? The challenge is the sheer quantity required. Saturn's rings are massive, but transferring enough material to Iapetus to build the ridge would be extraordinarily difficult. The orbital mechanics don't favor such efficient delivery. And even if the material arrived, it would have impacted at high velocity, spreading across the surface rather than piling up neatly along the equator. Some researchers have tried to address this by proposing that the ring material was particularly sticky or that it underwent some kind of processing after landing. Perhaps ice particles clumped together efficiently at the extremely low temperatures of Iapetus' surface. Perhaps the initial deposits were redistributed by subsequent geological activity. But these additions make the model more complicated and less testable. There's a variant of the ring hypothesis that deserves mention. What if the ring wasn't made of foreign material at all? What if Iapetus itself shed material into orbit, forming a ring from its own substance? This could happen through several mechanisms. A large impact could have blasted debris into orbit. Volcanic activity, if Iapetus ever had any, could have ejected material. Tidal forces from Saturn could have pulled material off the surface during close approaches, though Iapetus' current orbit makes this unlikely. If Iapetus did create its own ring, the material would have been similar in composition to the Moon itself. Ice, primarily, mixed with rocky silicates. This ring would have orbited in the equatorial plane and eventually fallen back to the surface, preferentially along the equator. The ridge would essentially be recycled Iapetus material, processed through a ring phase. This scenario is intriguing but speculative. We have no direct evidence that Iapetus ever had a ring. The surface shows no obvious scars from the violent events that would have created one. And the detailed structure of the ridge doesn't obviously match what we'd expect from accumulated ring debris. Let me turn now to some of the more exotic ideas that have been proposed. Science thrives on creativity, and the Iapetus ridge has inspired some genuinely imaginative thinking. One proposal involves the tidal heating of Iapetus during its early orbital evolution. If Iapetus' orbit was once more eccentric than it is today, the varying distance from Saturn would have flexed the Moon's interior, generating heat through friction. This tidal heating could have maintained a warm interior for longer than radioactive decay alone, allowing for more complex geological processes. In this scenario, the equatorial ridge might be related to patterns of internal heat flow shaped by the Moon's rotation and orbital dynamics. Convection currents in a warm interior could have been organized by the combination of rotation and tidal forces, focusing heat release along the equator. This could have produced volcanic activity or tectonic deformation preferentially in that region. The problem is that we see no clear evidence of volcanism on Iapetus. The surface appears ancient and heavily cratered, suggesting that any internal heat dissipated very early in the Moon's history. If tidal heating played a role, it was probably limited to the first few 100 million years, which might not be enough time to build such an extensive ridge. Another speculative idea involves the collision of Iapetus with another body during the chaotic early history of the Saturn system. In the first few 100 million years after the planets formed, the outer solar system was a violent place. Giant planets were migrating, smaller bodies were being scattered, and collisions were common. If a large impactor struck Iapetus at just the right angle, it could conceivably have deposited material along the equator or triggered tectonic activity concentrated in that region. This hypothesis has the advantage of requiring only a single event rather than sustained geological processes. But it struggles to explain the remarkable geometric precision of the ridge. Impacts are inherently random and chaotic. Even if an impactor happened to arrive in the equatorial plane, the resulting debris distribution would be irregular, not a neat line of mountains. There's also been discussion of whether the ridge could be related to the formation of Iapetus itself. Moons form through the accumulation of smaller bodies in a disk of material orbiting a planet. If this accumulation process was somehow asymmetric, concentrating material along the equator, it could potentially leave a lasting signature in the Moon's structure. Some models of Moon formation do predict equatorial concentration of material. Gas drag in the circumplanetary disk tends to pull particles toward the midplane, where they can accumulate more efficiently. If Iapetus formed from such a concentrated band of material, the core of the Moon might retain an equatorial enhancement that later influenced surface geology. But this idea runs into timing problems. The ridge appears to be a surface feature, not an expression of deep internal structure. Its formation required processes operating at or near the surface, not primordial asymmetries in the Moon's core. And the sharp, mountainous morphology of the ridge doesn't match what we'd expect from gradual internal differentiation. What about the composition of the ridge itself? Unfortunately, we don't have detailed spectroscopic data that would tell us exactly what the mountains are made of. From Cassini's observations, the ridge appears to be similar in composition to the surrounding terrain, primarily water ice with some rocky contaminants. There's no obvious signature of exotic materials that might indicate a foreign origin. This doesn't definitively rule out the ring infall hypothesis, but it does weaken one potential line of evidence. If the ridge had turned out to be compositionally distinct from the rest of Iapetus, it would have strongly supported an external origin. The fact that it matches the local material is more consistent with internal processes, though ring material derived from Iapetus itself could also explain the similarity. The temperature structure of the ridge offers another observational constraint. Iapetus is a cold world, but it's not uniform. The sun-facing hemisphere is slightly warmer than the dark side. The equator receives more sunlight than the poles. These temperature variations affect the behavior of ice over geological timescales. At the temperatures on Iapetus, water ice is extremely rigid, almost like rock. But it can still flow very slowly over billions of years, a process called viscous relaxation. Tall mountains should gradually slump and spread under their own weight, becoming lower and broader over time. The fact that the ridge has maintained its extreme height for billions of years tells us something about the mechanical properties of the material and the thermal history of the region. Calculations suggest that the ridge should be stable against viscous relaxation at current temperatures. The ice is simply too cold to flow significantly over the age of the solar system. But if Iapetus was once warmer, the situation would be different. A warmer ridge would have relaxed faster, potentially erasing the feature before it could be preserved. This constrains models of Iapetus thermal evolution, requiring relatively rapid cooling to lock in the ridge before relaxation could destroy it. Let me also address the broader context of icy moon geology. Iapetus isn't the only moon with unusual surface features. Enceladus has its tiger stripes, deep fractures near the south pole that spew water vapor and ice particles into space. Europa has its chaotic terrain, regions where the surface has been broken up and refrozen in jumbled patterns. Miranda, a moon of Uranus, has enormous cliffs and strange chevron-shaped features that suggest a violent geological history. Each of these moons presents its own puzzles, but none of them have anything quite like the Iapetus ridge. The tiger stripes of Enceladus are clearly related to tidal heating and cryovolcanism. Europa's chaos terrain reflects the interaction between a surface ice shell and a subsurface ocean. Miranda's features may record a catastrophic collision and reassembly. These phenomena have terrestrial or at least comprehensible analogues. The Iapetus ridge stands apart because it has no clear analogue anywhere. It's not obviously volcanic. It's not obviously tectonic in the familiar sense. It's not obviously impact-related. It exists in a category of its own, forcing us to consider processes that we haven't encountered before or combinations of processes that we haven't previously imagined. This is precisely what makes it so valuable scientifically. The ridge is a window into physical mechanisms that we don't fully understand. Solving the mystery won't just tell us about one moon's history. It will expand our understanding of how worlds work in general, adding new tools to our geological toolkit that might explain features elsewhere in the solar system or beyond. There's a philosophical dimension to this as well. The history of planetary science is largely a story of discovering that Earth is not special. The same processes that shape our world, volcanism, tectonics, erosion, impact cratering, operate throughout the solar system and presumably throughout the universe. But every once in a while, we find something that genuinely has no terrestrial equivalent, something that reminds us that the universe contains possibilities we haven't dreamed of. The Iapetus ridge is one of those humbling discoveries. It tells us that our imagination is limited, that nature can still surprise us fundamentally. We look at this perfect line of mountains and realize that 4.5 billion years of history have left us a puzzle we can't yet solve. The universe has secrets, and some of them are carved in ice and stone on a distant moon. 1519 The story of the Iapetus ridge is, in many ways, the story of science itself. We observe something unexpected. We propose explanations. We test them against the evidence. We refine our ideas or discard them entirely. And sometimes, despite our best efforts, we're left with honest uncertainty. Not because we've failed, but because the universe is genuinely complex and our data genuinely limited. What we do know is remarkable enough. We know that 4 billion years ago, something extraordinary happened on this small, frozen moon. Forces of almost unimaginable magnitude sculpted a mountain range twice the height of Everest along a perfect geometric line. Whether those forces came from within, driven by the slowing spin of a young world, or from above, delivered by a transient ring of debris, the result was the same. A monument was built, a testament to processes we're only beginning to understand. And that monument has survived. Through 4 billion years of meteorite bombardment, through the slow dance of orbital mechanics, through the patient accumulation of dust from distant Phoebe, the ridge has endured. It will likely endure for billions of years more, long after human civilization has risen and fallen and risen again, long after our sun has exhausted its fuel and swollen into a red giant. The mountains of Iapetus will still be there, still tracing their perfect line around the equator, still keeping their secrets. There's something profound in that permanence. We build monuments on Earth to preserve memory, to assert that something mattered, that someone was here. But our monuments crumble. The pyramids are slowly dissolving. The great statues are wearing away. In a few million years, nothing we've built will remain recognizable. Yet the ridge of Iapetus, built by no one and for no purpose, will outlast every human creation by orders of magnitude. Perhaps that's the final lesson of this strange feature. The universe doesn't need us to be magnificent. It produces wonders on its own, casually, as byproducts of physics and chemistry and time. Our role is not to create meaning but to discover it, to look at a line of mountains on a distant moon and feel the weight of cosmic mystery pressing down on us. When Cassini sent back those first clear images of the ridge in December 2004, a small group of scientists gathered around computer screens and stared in disbelief. Nothing in their training had prepared them for what they were seeing. Nothing in the long history of planetary exploration had hinted that such a feature could exist. They were witnessing something genuinely new, a discovery that would reshape their understanding of what moons could be and what forces could shape them. That moment of wonder, that instant when the unknown becomes visible, is what drives exploration. We send spacecraft to distant worlds not because we know what we'll find but precisely because we don't. Every mission is a gamble, a bet that the universe has surprises waiting for us. The Iapetus Ridge was one of those surprises. There will be others. Someday, perhaps, a spacecraft will orbit Iapetus, mapping its gravity field and probing its interior. Someday a lander might touch down on the ridge itself, analyzing rock samples and measuring the composition of those ancient mountains. Someday we might finally know how this impossible feature came to be. But until that day, the ridge remains what it has always been. A question written in ice and stone. A challenge to our understanding. A reminder that the solar system, even after 6 decades of exploration, still has the power to astonish us. The mountains of Iapetus don't care whether we understand them. They simply exist, tracing their eternal line around the equator of a frozen world, waiting for someone to read the story they tell. That story began 4 billion years ago, in the chaos of a young solar system, when forces we can barely imagine shaped a world in ways we still can't explain. And the story isn't over. It continues every time a scientist studies the Cassini data. Every time a student writes a thesis on tidal depinning. Every time someone looks up at Saturn through a telescope and wonders about its distant, mysterious moons. The ridge is part of our story now, woven into the human quest to understand our place in the cosmos. We are small creatures on a small planet, gazing outward at wonders we can barely comprehend. But we gaze nonetheless. We ask questions. We build spacecraft and write equations and argue about ring infall versus depinning. We refuse to accept mystery as the final answer, even when mystery is all we have. That refusal, that stubborn insistence on understanding, is perhaps the most human thing about us. The Iapetus ridge doesn't need to be explained. The universe doesn't owe us answers. But we seek them anyway, driven by a curiosity that defines our species. And so the ridge waits, patient and eternal, holding its secrets beneath the dim light of a distant sun. One day we will understand it. One day the mystery will yield to knowledge, and we will add another chapter to the long story of discovery. Until then, the mountains stand. 20 kilometers high. 1,300 kilometers long. Perfectly aligned with the equator of a world that shouldn't exist. A puzzle, written in stone, waiting to be solved. Claude is AI and can make mistakes. Please double-check responses.